Welcome back. It's time for us to begin the next portion of our lesson. So that's all fine and dandy, but how are we going to find the actual components in numbers? Well, one thing I hope you've picked up on so far is every time I broke a vector into components, I formed a right triangle. For example, take a look right here. When I broke this vector A into components, I had a right triangle, and here was my right angle, my 90-degree angle. Well, we're going to have to understand a little bit of right triangle geometry in order to figure out how to come up with exact numbers for the components. And here's how we're going to do it. We're going to use a little trigonometry. Now, you all have seen this before in your geometry class. May have been a year or two, but you've seen this before. And if you're taking pre-calc now, you're going to be using this a lot. But just in case you don't remember, let's do a quick refresher on sine, cosine, and tangent. The sine of an angle is simply the ratio of the side that is opposite that angle divided by the hypotenuse, which is the longest side. If you take a look here at the picture on the left, my angle theta is right here, and the side that's opposite to that angle is A. Meanwhile, the hypotenuse has been labeled with C. Therefore, the sine of this angle theta is A over C. The cosine of an angle is the adjacent side over the hypotenuse. Adjacent means the side that is not opposite and it's not the hypotenuse. Well, that's going to be this one, B. The hypotenuse, again, is the longest side, C. So the ratio that is called the cosine of theta in this case is B over C. Finally, the tangent of the angle theta is simply the opposite side over the adjacent side. So that's A over B. And the great thing about right triangles is that any right triangle that has the same breakdown in terms of angles, so all similar triangles will have exactly the same ratios. And your calculator can find all those ratios for you and allow you to go back and find sides and so forth. Now, one thing you might want to note, whether or not I use the sine or the cosine depends on which angle I'm looking at. I mean, for example, if I labeled this angle as x, then the sine of x would be the opposite over the hypotenuse. And the opposite side to x is actually b here, so it would be b over c. So which ratio, which side you're using, depends on which angle you're looking at. Here's the big idea. Anytime we have a right triangle, which is what we're going to have anytime we break a vector into components, as long as we know either two of the sides or one of the side and one angle other than the 90-degree angle, we can use our trigonometry to find everything else about that triangle. Very important tip. You're going to have to use your calculator to do this. And when you use your calculator, because we're always going to be working with degrees, angles in degrees, you want to make sure that your calculator is in degree mode. If it's set to radian mode, you'll get the wrong answer. So double check that every time. All right, now let's apply what we've learned to the right triangle you see in this example. So you'll notice that we've got two sides given, side 20 and side 40. The 40 side is the hypotenuse because it's the long side, and we don't know the third side. We're going to find that in a second. You'll also notice that I've already labeled the right angle, and then the other two angles are unknown, and they're called little a and little b. Let's start by finding side A. To find side big A, I'm going to use the Pythagorean theorem, and I'm going to note that 40 squared, which is the hypotenuse squared, should equal big A squared plus 20 squared. This means that 1600 equals big A squared plus 400. Therefore, big A squared is equal to the square root of 1200, which is equal to 34.6. So I'm going to go ahead and put that here on the picture. 34.6 is big A. All right, now let's go and solve for the missing angles. Let's start with little a. Angle little a. I now know all three sides. How could I find A? Well, all I need to do is write down some trig relationship that involves little a and two sides that I know. So, maybe I pick the sine of little a. And I say that the sine of little a is equal to the opposite over the hypotenuse. And for little a, the opposite side is 34.6. That's the one I found just a minute ago. Side big A, 34.6. The hypotenuse is 40. And if I plug this into my calculator, 34.6 divided by 40 is 0.865. Okay, what this means is that the sine of my unknown angle equals 0.865. Well, how do I find my angle then? Well, the good news is your calculator can do this for you. The way it does it is by finding what they call an inverse sine or an arc sine. And here's the way it will normally look on a calculator. They'll either write it as the inverse sine with a -1, or you may see it as an arc sine. And sometimes they'll just use a sine for arc sine. It all means the same thing. So I want to do this inverse or arc sine. And what do I put as my input? What the sine actually was, 0.865. That was my ratio. The sine was 0.865. And if I plug the inverse or arc sine of 0.865 into my calculator, and I'm careful to make sure I'm using degree mode, it will give me the right answer. Let's do that now. All right, now let me show you how to evaluate an arc sine or inverse sine using your calculator. Here's a scientific calculator that looks like a pretty standard scientific calculator. And if you notice, over here on the left, I have sine up. That's typically sine, cosine, tangent are all right here. These are typically what you're going to see on your calculator. Now, to get to the inverse sine or inverse cosine or the inverse of any of these functions, what's going to take you from the sine, cosine, or tangent, if you know it, back to the angle? In order to do that, you typically just have to hit something like second or a shift, and then the button that corresponded to your trig function. So here I hit second sine, and it gave me arc sine. Now, all I have to do is enter in what the sine was. It was 0.865, and then hit enter, and it tells me right up here at the top that the angle is about 60 degrees. So apparently, angle A, the arc sine or inverse sine of 0.865 is 59.9 degrees, pretty close to 60. Now it's pretty easy to find what angle B is because I know that A and B have to add up to 90 degrees. So angle B must be 90 degrees minus 59.9 degrees, and that's about 30.1 degrees, just like that. Now, one thing I want you to notice is I didn't have to use sine. I could have used an inverse tangent or an inverse cosine, and it would have worked perfectly fine. Let me just show you how I would have written that very quickly. If I wanted to use tangent to find A, I would have said the inverse tangent of, and then for A, I'd say the tangent is opposite over the adjacent. That would have been 34.6 over 20. And if I entered this in my calculator, I would have gotten back the exact same angle A. And you could have done the same thing with an inverse cosine. All right, let's move on. All right, let's take what we know now about right triangles in trigonometry, and let's apply it to vectors to find the components, those x and y pieces that make up the total vector. So here I have a velocity vector, and yes, velocity is a vector. And this velocity vector has a magnitude of 40 meters per second, and the direction is given by the direction of the vector arrow. You'll notice that I've labeled an angle here of 35 degrees. Let me go ahead and draw in the two components. There's my x component, so I'm going to call this Vx. Notice it goes as far left or right as the whole vector does. Now let me draw in the y component. It's going to go straight up or down from there. In this case, it goes up. And there's my y component, Vy. Now before I do any calculations, I can tell immediately that because Vy points upwards, it's going to be positive according to our sign convention. And because Vx points to the left, it will be negative according to our sign convention. It's very important that you get the signs right because your calculator, when you enter an angle like 35 and use sines and cosines, will always give you a positive answer so long as your angle is less than 90. So you need to get the sign right yourself. Be very careful. All right, now let's go see if we can figure out what Vy is, what my y component is. Well, Vy, you'll notice, is opposite the 35-degree angle. Well, which side do I know? Well, I know the hypotenuse. That's the magnitude, 40. So I need to tie together a 35-degree angle, a hypotenuse, and an opposite. How do I do that? With the sine. I say the sine of 35 degrees is opposite Vy over hypotenuse, which was 40. meters per second. And now you'll notice I can very easily manipulate this equation to give me Vy equals 40 meters per second times the sine of 35 degrees. And at this point, I can go back to my handy calculator and it will do the work for me. I have 40 times the sine of 35 degrees. Just like that. And if I hit enter, it tells me that the answer is 22.9. So apparently, my Vy, my y component of the velocity, is 22.9 meters per second. And again, it's positive. Now I'm going to do a similar step to find the x component, but this time I'm not going to use sine because the x component of my vector is not opposite to the 35-degree angle. It's adjacent to it. So I need to use cosine. So let's try that. The cosine of 35 degrees is adjacent side over hypotenuse. And in this case, my adjacent side, if you go back to the picture, that's your Vx. Remember, that's the side that's not opposite and not the hypotenuse. Well, that's what I'm looking for. So Vx is my adjacent. The hypotenuse was 40 meters per second, as we saw a minute ago. So apparently, the cosine of 35 degrees equals Vx over 40 meters per second. Therefore, if I rearrange, Vx is equal to 40 meters per second times the cosine of 35 degrees. And if I plug this in my calculator, 40 times the cosine of 35 degrees, I get an answer of 32.8. So apparently, Vx is 32.8 meters per second. Now, if I stop there, I actually wouldn't have the correct component, because if you go back and look at my picture, as we discussed just a minute ago, my Vx points to the left. It's negative. The calculator didn't know that. It thought it was solving a triangle. So I need to make sure to add that negative sign myself. This isn't a brainless step-by-step process. It involves a little bit of thinking. All right, let's take a look at what we found. We found that we have an x component of negative 32.8 meters per second, and we found a second ago that we had a y component of our velocity that was equal to a positive 22.9 meters per second. I'm going to go ahead and label these 22.9 and negative 0.8. One thing I want you to notice is 22.9 and 32.8 are both smaller than 40. Exactly what you would expect, since this looks like a right triangle. The other thing that I want you to note is, if I took my 22.9 and squared it and added it to negative 32.8 squared, using the Pythagorean theorem, I ought to get 40 squared. I'm not going to take the time to do that, but you can feel free to do that yourself if you'd like. All right, let's move ahead. Let's try an example. I have a skier that travels 100 meters down a slope that makes a 20-degree angle with the horizontal. What are the skier's x and y displacements? Now, there's some very careful language in here. They tell you that the slope makes a 20-degree angle with the horizontal. You got to realize every time we have a problem, there's lots of different angles involved, and you have to be very careful that you're labeling the correct angle. Now, horizontal means level with the ground. So in this case, it would be what's running left to right, like our x direction. So the horizontal looks sort of like this. They tell us that the slope makes a 20-degree angle with the horizontal. Well, since it's less than 90, that's got to be this angle. A 20-degree angle with the horizontal has to be this one. So I'm going to label this as 20 degrees. Okay. Now I want you to note they could have described the angle differently. For example, they could have told us that it's a 160-degree angle measured from the positive x direction. And that would mean start this way, which is positive x, and rotate back 160. And you'll notice that if I did that here, and I went back 160 degrees to there, that would correspond to this being a 20-degree angle. And there are many other ways it could be described as well. Our general convention in this class is going to be that if you're not given any indication as to how to measure the angle, they just say that there's a vector at a 30-degree angle and they tell you nothing else, then you're going to measure it from the positive x direction, or from the right, counterclockwise, just like this. However, in many cases, you will get a better description and it'll be a lot more obvious, like it is in this problem. So let me go ahead and erase that extra stuff that we don't need. And let's see if we can solve this problem. So we've labeled our angle as 20 degrees. We're asked to find the x and the y components, so we need to draw these. Does my skier have a displacement up the slope or down the slope? They didn't draw an arrow for me, did they? Well, it's a skier, and it says that he travels down a slope, so his displacement is apparently along the direction of the slope and downwards, like this. Just like that. That's his total displacement. And that displacement is 100 meters. It has two pieces. If you take a look at this arrow that I've drawn, it consists of a combination of downwards and to the right. The to the right part is the x component, and I'll call this delta x to be consistent with what we've called displacements in the past. The downwards part I'm going to call delta y to mean change in y, because we usually call y the variable up down. So this will be y displacement, x displacement, and the y displacement is just the y component of the total displacement, while x displacement is just the x component. We got two pieces now to the total. All right. If I take a look here at my picture, my y displacement should be negative because it points down, and my x displacement should be positive because it points to the right. Now let me go find the values. Let's give ourselves a little bit of room to work with. I'm going to redraw very quickly our picture, just like this. We have 100 meters. We have a 20-degree angle. We've got a negative y displacement, and we have a positive x displacement. All right. Let's see if we can find delta y, or y displacement. Well, it's the side opposite an angle that we know, the 20-degree angle. And I know the hypotenuse, so I need to use opposite and hypotenuse. So I'm going to use the sine. So here's how I'm going to do it. I'm going to say that the sine of 20 degrees is the opposite side, the y displacement, over the hypotenuse 100 meters. And if I rearrange, I have delta y is 100 meters times the sine of 20 degrees. And if you take just a moment and you put that in your calculator, you'll come up with 34.2 meters. And again, since it's downwards, it must be negative. I have to add that sign myself. How about the x displacement? Well, let's do something a little fun. Let's use this angle. If this is a right angle, this must be 70 degrees. I'm going to try that one out. How could I come up with this? I know what I'll do. Now that I know delta y, and I want delta x, I'm going to use opposite and adjacent. Let's try using the tangent just for fun. The tangent of the 70-degree angle should equal the opposite side, and the side opposite the 70 is my x displacement, over the side adjacent to my 70-degree. Remember, that's the one that's not opposite and not the hypotenuse. That's my y displacement. Now, be careful. Your calculator thinks you're still dealing with a triangle. So you need to drop the negative sign from your delta y as you do this, because you need everything to be positive when you put it in your calculator. You've got to go back and get the sign on there later. If I rearrange this, what this tells me is delta x equals delta y times the tangent of 70 degrees. And if I plug this in my calculator, I come up with 94 meters. Should it be positive or negative? I just have to look at my picture. My x displacement's to the right, it's positive. See how I would have made a mistake if I'd put a negative in for my delta y? The negatives and positives you always get by looking back at your picture. Always. Alright, it's time for a short break and an opportunity for you guys to check your understanding by doing the prep check questions on what we've done thus far. Once you've completed those questions, which immediately follow this video, inside your assignment, you can proceed to the next video where we will continue our study.